Hi everyone. Imagine taking a casual video with your phone and being able to reconstruct the 3D structure of the scene even if people or objects are moving. That's exactly what MegaSaM paper achieves, which is accurate, fast and robust structure motion from dynamic videos. Let's find out how. Before that, just I want to introduce topics such as SFM, SLAM. We all know they are nothing but extracting camera motion and 3D scene structures from videos. They work well for static scenes with strong camera movement. What about if they are dynamic in real videos? I mean in real world scenarios. Camera often moves, has various focal lengths and scene contains moving objects. I think this condition breaks for traditional methods. Am I correct? Now, how can this problem will be solved? Recently, many attempts are you tried to fix this using depth networks, radiance fields, global optimization, but they are usually slow, fragile, and struggle with long videos. Now let's come to about paper abstract. Overall, MegaSaM is nothing but it delivers a practical and robust solution for tuning everyday handheld videos into accurate 3D reconstructions, even in challenging real world conditions. We all know neural networks based methods try to solve these problems, but they can be slow. So, here the MegaSaM, MegaSlam plays a major role in solving these dynamic scenes. Here they trained on synthetic and both real data. Let's get an introduction about this MegaSaM. MegaSaM is nothing but a complete pipeline that extends a digital visual SLAM, nothing but dried SLAM. It's also a paper published in 2021 to handle casual in the world monocular videos with dynamic scenes and unknown focal length. Here key innovations are nothing but predicting per pixel motion probability maps to downweight dynamic regions in a differentiable bundle adjustment loop. Here differentiable bundle adjustment loop is nothing but a optimization technique, and monocular depth initialization for disparity or camera initialization, and uncertainty aware global BA that decides when to add the mono depth regulator. It depends on based on SN or observability matrix. After camera tracking, MegaSaM optionally runs a fast first ordering CVD optimization, nothing but consistent video depth optimization by fixing cameras to produce temporarily consistent high resolution videos. This is the case how MegaSaM will play key role. In the top we see that input video frames, every 10th frame has shown, nearly 5 frames are shown for every 10th frame. Then after bottom is our estimated camera and 3D point clouds and projected by a predicted video depths without any pre-processing. Now let's talk about related work which are needed. Here when we are constructing 3D reconstruction, 3D scene reconstruction needed basically have needed the topics such as visual SLAM and SFM. SLAM is nothing but simultaneous localization and mapping, and SFM is nothing but structure from motion. These are helpful. These are helpful in extracting camera motion and 3D structures from the videos. Next, we have to know about monocular depth and dynamic scene reconstruction. Now let's go what is meant by visual SLAM and SFM. SLAM and SFM are used to estimate the camera parameters and 3D scene from the video sequences, as we discussed before. Conventional approaches tackle this problem by first estimating 2D correspondence between images through feature matching. Then they optimize 3D point locations and camera parameters by minimizing reprojection error through optimization algorithm bundle BA. Recently, SLAM and SFM are adopting deep neural networks to estimate pairways or long-term correspondence to reconstruct the redensity or global 3D point clouds. While these methods demonstrate accurate camera tracking and reconstruction, but they work with respect to static scenes, which performance degrade when it comes to dynamic scenes. So, how we can solve the dynamic scene problem? Here, this limitation is addressed by robust CVD and casual SAM, jointly estimating camera parameters and dense depth maps from dynamic videos by optimizing a spatially varying spline or fine-tuning molecular depth networks. Even though these are used robust CVD and casual SVM, but regarding dynamic videos, they have downweighted the features on further tracking. So to overcome this, our SAM paper uses similar ideas, but the performance can be significantly improved by coupling differentiative SLAM system with intermediate prediction of underlying dynamic scenes. Next, monocular depth. Recent work on monocular depth prediction has shown strong generalization on in the wild single images by training deep neural networks on large amount of synthetic and real world data. However, these single image models tend to produce temporally inconsistent depth models by performing test time optimization or to use transfer or different model to directly predict video depth. This is the same paradigm we use here to achieve better video depth without expensive network for fine tuning every video. Next, dynamic scene reconstruction. It's nothing but a reconstructing a 3D scene, even even though scene is dynamic. Here, techniques uses since most radiance field reconstruction methods required camera parameters or video depth as input and and our output can be used as an input to the system. Next, MegaSaM typically constrained continuous video sequence, which here I nothing but image, where H and W indicate height and width of that image. For that image, there are number of for the video we have number of frames. Each frame is taken as I. Our goal is to estimate camera pose and focal length, which is unknown, and dense video map. Our approach does not pose any constraint on camera and object motions present in the input video. Our camera tracking and video depth estimation modules build upon prior deep visual SLAM, which is nothing but dried SLAM and a casual structure and motion framework respectively. Here dried SLAM is model which they have taken from deep visual SLAM for monocular stereo and RGB cameras, advances in neural information processing system, which is published paper of 2021 by Jagri, Teed and Giardeng. Now let's dive deep to what are the components in deep visual SLAM formation. Deep visual SLAM systems like dry SLAM are characterized by a differentiable length bundle adjustment BA layer which iteratively updates structure and motion parameters. In particular, they keep track of two state variables for a video, a per frame low resolution depth map and a camera poses. Here you have to note that in dried SLAM is inputting H cross W and giving an output of size of H by 8 cross W by 8, and during inference stage through differentiable BA layer which operates over a set of images pairs for a both images I and IJ, but build it to connect frames with overlapping field of view. Here, first equation of derives the determines the dried slam lens to predict the 2D correspondence between two video image frames, which which gives the corresponding field and confidence through gated recurrent units iteratively. So we get the rigid motion correspondence field for derived from a ego motion as the disparity as uij equal to phi of g cap ij phi inverse pi dA k inverse of k. Here pi nothing but a grid of pixel coordinate, pi denotes perspective projection and g denotes gij denotes pose relative camera between ia and ij frames. K is a camera eccentric matrix, nothing but a camera parameter. Then after second, differentiable bundle adjustment. I have already previously said differential bundle adjustment is nothing but an optimization technique which is used in dried slams to update the camera poses and depth map and focal length at every iteration step. Here assumes known as dried slam assumes known focal length, but focal length is typically not known a prior in the wild videos. Therefore we optimize camera pose, focal length and disparity by iteratively minimizing the projected weight cost between current flows predicted by the network and rigid mode motion ones derived from camera parameters and disparity. This is the rigid motion which is derived from camera parameters and disparity of which is second equation, and summation over ij is diagonal of weighted over inverse to enable the differentiable end-to-end training. And we also used the Levenberg-Markman algorithm for optimization, which in this network is iterated. I mean BA, for every BA iteration, diagonal matrix contain WAJ from each pair. Lambda is a damping predicted by network during each BA iteration. We can separate camera parameters including poses and focal length and disparity variables by dividing Ascent matrix on LHS. Here HGF is a Ascent matrix with respect to pose and focal length. Now we apply here scalar complex trick which leads to fully differentiable BA bundle adjustment optimization algorithm. The training flows goes like L static is equal to L cam plus W flow into L flow. Here L cam and L flow are the losses comparing estimated camera parameters and ego motion included flows from the BA layer. It's this is the first part of training, which is nothing but a static training, which is done on dried slam. Here we have seeing three pictures. They are nothing but considered as a first picture, which is without mono depth initialization, and compare it with second one, which is without uncertainty over bundle adjustment BA optimization bundle adjustment. Then third one with the full configuration. Here we can see our full method produces much better camera and scene geometry when compared to A and B. Now second one, scaling to in the wild dynamic videos. Previously we discussed about static videos. Here it works for static videos during training and first stage. What about the input is a dynamic video? So for the dynamic video, how they intended to approach this model to get rid of model performance degradants means They proposed the key modification to original training and inference pipeline. First, their model predicts object movement maps that are linked together with a flow and uncertainty in order to downweight dynamic elements within the differentiable BA layer, bundle adjustment layer. Second, they proposed to integrate pairs from the monodepth estimates into the both training and inference pipeline and perform uncertainty aware global BA, both of which aid disambiguation of object and camera motion in challenging casual dynamic videos. Here, this system is trained on synthetic data alone, but they demonstrate its strong generalization to real-world videos. So, they have trained completely on synthetic data for dynamic videos, which is later adapted to real-world videos. Now, how training is done. First of all, I'm gonna discuss. About what is the data set. Here, data set they have taken. Here, data set has taken. Here, they taken tartan air and carbostatic as a static video data set, which is from tartan air. They have taken static scenes and curtain static from 5,000 videos, and Curbic dynamic as a dynamic videos dataset with 11K videos. Now, for validation dataset, they have taken Sintel, Diecheck and in the wild videos and used a metric of ATE, RT and RE, nothing but absolute trajectory error, relative translation error and rotational error. And how the data preparation has done. They have frames are resized uniformly and generate mono depth using depth anything and generate metric depth using uni depth and align depth distribution, build motion ground truth for dynamic scenes, extracting 7-frame sequence for training. That means for training they are taking only 7-frame sequences. Now, how our architecture look like. Our architecture has majorly consists of 8 modules. First module is nothing but a feature encoder and second module is context encoder. Here in the right we can see feature and construct encoders, which extract low resolution features from input video frames of original resolution. Here con block, residual block and residual block and final con. This act as a feature context encoder. Now we dive deep to what he meant by feature encoder. Here feature encoder uses a 5 to 6 residual blocks, extract deep features and output a H by 8 W8 and CF encoded features. Then context encoder is provide context for conv ZRU and output same shape as H by 8 and W8 into C. Now third one, correlation volume. Correlation volume is nothing but a dot product between feature of frame I and J. And 4D volume used for depth motion estimation. Let's discuss another module, update module, which is nothing but a conv ZRU, which takes features, correlation and previous flow along with context to get the output of updated flow and updated confidence set and hidden state. Now let's discuss of differential bundle adjustment, which is nothing but optimization technique. Differential optimization technique which updates camera poses, disparity and focal length at every iteration, which uses LM optimization with the scroll component. We already discussed it. This here. LM third equation which shows LM algorithm and a scroll equation which is nothing but a fifth equation which shows scroll component trick. This is what it discussed. Then motion probability module. Motion probability module predicts the dynamic objects region, which outputs the movement probability mask, means nothing but a motion mask, which downweights the dynamic pixels during bundle adjustment optimization algorithm. Next, depth initialization, mono depth initialization. Here depth anything indicates relative depth. Here I already discussed generate mono depth using depth anything. Here for my data pre-processing step, I generate mono depth using depth anything, which gives the details of relative depth, and generic metric depth using uni depth. Here uni depth gives the both metric depth plus focal, and we combine both depth anything and uni depth to align disparity, and then we downsample to our required h by 8 comma w8 by 2, integrate both feature encoder, context encoder and mono depth initialization to align together. Now uncertainty aware global BA, which is nothing but SN diagonal over h comma t. If depth is unobservable, motion depth is prior, and if focal is unobservable, freeze focal update. This is the architecture of flow of confidence and movement map predictor. Here gray blocks belongs to the network F for flow and confidence prediction, and blue blocks belongs to the network FM for object movement and map prediction. In first stage we perform ego motion pre-training for F. In second stage we perform dynamic fine tuning for FM. Here first stage we perform ego motion pre-training for F module, and second stage we perform dynamic fine tuning for FM module while fixing the parameters of the F. Means nothing but freezing the F. We are fine tuning the FM for dynamic fine tuning, I mean dynamic scenes. Okay, here context vector and correlation features are combined to pass to this, and along with the flow at step k and hidden step k to the GRU to get the flow at k1 and confidence at k1. Nothing but we are passing features correlation and feature map along with the previous content and context to ZRU, which is giving output as updated flow, updated confidence and hidden state, updated flow, updated confidence and hidden state. Here first stage is nothing but SLAM, DRUD SLAM, which is used for static scenes. Gray one is used for the static scenes. Then over they applying spatial spool, and then they are adapting to dynamic scenes by giving that spatial spool to convolution layer along with output of the ZRU confidence score along with confidence score, then temporal pooling to get the movement map. Means here blue one indicates FM module and gray one indicates F module. Okay, here F module is trained on static scenes and blue module is signed on dynamic scenes to get the motion map, and first one is to get the flow and confidence. Now let's talk about training. We all know input is nothing but a monocular video frames. Here stage 1 we do camera tracking by a differentiable BA. Second stage we do high resolution consistent depth optimization step. We need outputs camera poses, focal length and consistent metric depth maps. I already said regarding this. Here gray stage is static training and which is used for static scenes, and blue one is dynamic training which is used for dynamic scenes. These are the modules which are used for our entire architecture. Now first one input I already said for between data preparation extract exact 7 frame sequence for training as a last step. So we are inputting 7 frame sequences and extract features, and we build a correlation and iterative to update the flow and confidence, which is the output of ConvZRU flow at k step and confidence at k step 1, and we apply BA bundle adjustment for to update both pose and disparity. Now here we uses losses of flow loss and camera reprojection loss. Here the entire module is F module, which is nothing but a gray module. Here gray blocks is nothing but a F module. Then after training step stage 2, here our gray is entirely freezed. Then we are training new FM module, which is here blue module for dynamic videos. Here data is dynamic scenes from Kubrick dynamic, And our static scenes are nothing but turning air and cubic static. Here output is motion probability map, which is nothing but a movement map at k step 1. Then purpose is nothing but downward moving objects. Moving objects downwards we need it. Here differential BA objective is to reproject the loss compared predicted correspondence and geometric map. Is nothing but weighted using land confidence maps. Next, correspondent geometric correspondence equation we already know. UI is a which used for predicting pixel displacement for multi-view geometry. Then LM optimization, uh, which state vectors indicate poses, focal length and disparity. Then scalar complement to get the fully differentiable BA. We are using this scalar complement technique to get the fully differentiable bundle adjustment, which is used to efficiently solve the BA system. Then hyperparameters in our training are updated iterations k, which are 8 to 12, workflow, W prior and W temp and W motion. We use Adams optimization. Front end W2 they use it 0.05, and back end they use focal threshold and BD depth, and threshold depth as 1e minus 4 and focal depth as focal threshold as 50. Now we have discussed about datasets, data preparation, validation, then after modules architecture, then how the architecture flows and how the training will take place. Now we already seen our training stage static scenes, which uses 163 scenes from train year and 5k videos from static. In second stage we fine tune the motion module FM on 11k videos from Kubrick. Each training example consists of 7 frame video sequences. We pre-compute a distance matrix between each pair of video frame based on the average ego motion including flow magnitude. We then dynamically generate a training sequence according to the constructed distance matrix. We randomly sample each training sequence according to the constructed distance matrix. We randomly sample each frame such that average flow between them is between 0.5 pixel and 64 pixel. Within the camera tracking module, we normalize video disparity D such that its 98% is 2, which also normalize focal length by dividing it by input image resolution within every bundle adjustment. This should be followed in entire paper during both training and inference. Now let's talk about inference. Here inference is consist of 3 phases. First phase is nothing but computing mono depth, which is nothing but mono depth pre-processing. I have already discussed depth anything which gives relative depth, unit depth which gives metric depth plus focal, aligning depth for disparity in it, which I already shown in data preparation. Generating mono depth using depth anything, generating metric depth using unit depth, and aligning depth distributions. Then second step we have to do is computing focal estimate. Then we get here disparity, initializing disparity and pose. Now downsample the disparity. This is the first stage pipeline. Next second phase pipeline is nothing but camera tracking. Here feature encoding means extracting features by feature encoding. Feature encoding is, I have already said, feature in this modules feature encoder and context encoder are used to get the feature extracted. Modules are used to get feature extract features, which is the first step feature encoding. Then after correlation computing to build correlations, which is nothing but here correlation volume, which is a dot product between features of frame I and I, which we get 4D volume used for motion estimation. Then motion iterative BA to update the pose and disparity and focal at every step, bundle adjustment optimization algorithm. Then after motion mask is applied to get the filter dynamics, keyframe selection plus global BA. Okay, then third step, inference pipeline phase 3, which is optional CVD depth refinement. Here it optimizes both disparity and uncertainty. Losses here temporal consistency and flow reprojection. Here we use multi-frame optimization for smooth depth, and we get the high resolution depth maps. Here I'm gonna dive deep What is meant by mono depth initialization? You mono depth initialization means uses depth initting relative and unit depth metric. They which metric aligned via scale and shift alpha b. Here alpha b are hyperparameters, um, hyperparameters. Then critical for low parallax sequences. Then next, front end optimization. Here front end optimization is nothing but pose only BA estimation, means applying sliding window on mono depth regularization, means which uses reprojection and depth with alignment, depth alignment, which is required for inference pipeline phase 1. Now we gonna deep for inference pipeline phase 2. We already know feature encoding, correlation computation modules. It raises BM update to update the pose disparity and focal length. LM iterate to BA to get the and geometric correspondence equation, and LM optimization formalization at a down and scalar complement, which update pose and a depth map at a training. Now we already know iterative BA updating. Then after we have to know what is backend global BA, means bundle adjustment. It fixes or corrects the poses globally, uses SN matrix diagonal to evaluate observability, which adapt mono depth, weight, and focal optimization. What is uncertainty estimation via ASN means large uncertainty describes depth and unobservable, which describes increased prior weight, which able to detect the non-observable focal length. Now what is CVD? Consistent video depth module. It optimizes the high resolution depth DI, fixes camera poses to get the stable refinement, object to include flow, temporal and mono depth prior. Here in phase 3 we uses three losses, temporal consistency, sorry, two losses, temporal consistency and flow reprojection. Here temporal consistency loss uses scale invariant depth difference, which encourages temporal smoothness, uses raft for correspondences of two frames, and flow consistency loss is nothing but which is a heterosectic uncertainty formulation which controls the influence of unreliable flow regions. This is the inference pipeline which I have discussed. Now this is the training pipeline. This is our module, entire module, which consists of F for static scenes, gray, and blue FM module for dynamic scenes. And these are the modules they used, and which is the data set, data preparation, validation, training detail. Now let's gonna dive deep how to implement this thing. Here MegaSystem separates the problem of camera and scene estimation into two stages we already discussed. In particular, we first estimate the camera poses, focal length and low disparity from input modality video through differentiable bundle adjustment, where we initialize D with monocular depth maps predicted from off the self modules. In second consistent video depth phases, we fix the fixed camera parameters and perform first order optimization or video depth and uncertainty maps by enforcing flow and depth map losses included by pairwise 2D optimal flows. Here framework we include at a static stage is DietSlam, which is nothing but here gray one, along with BA optimization bundling algorithm technique to iteratively update the flow confidence and molecular probability prediction at each input to model pair of video frames. Then after we use context and feature encoder to encode each input with frames into depth resolution, then correlation feature maps, then we apply iterative updates, then consistent video depth. This which we already discussed here, which modules feature encoder. If I doubt, you can refer previous which I discussed previous 5 minutes back, each module feature and construct encoder. Then yeah, now what is training? Training I already discussed disparity and camera initialization, which have Dryad-Slam image motion probability over which during training, how d with disparity from depth anything is used, and how training sequences for two camera process to remove ground truth ambiguity and focal length ground truth value by 25% is also we have token. Now inference frameworks also front end module, back end module, which is front end module keyframe selection plus sliding window BA, and backend module is global BA over it. We already talking at inference pipeline at phase 1, phase 2, phase 3, which is CVD module, which is completed. Now here uncertainty global BA module, which is a global BA over all frames, has shown, and the equation 9 shows at the mono depth regularization into global bundle adjustment, and here figure 2, if a video is captured from a rotational camera with little camera baseline, then performing a reprojection only BA without additional content that lead to degenerated solutions. You can see by here figure, we can see third one full gives the good when compared to both without uncertainty B and without a mono depth initialization. Now this is the essential matrix. We can use Laplace approximation to estimate the covariance of our variable to essential matrix, which is computationally high. Now we can also discuss it during inference at a third stage. During inference we have discussed at third stage CVD, optional CVD depth refinement, which fixes the camera poses with a stable alignment, and objective is to get a temporal flow and mono depth prior. We usually a temporal consistency loss and flow consistency loss, which is discussed here. Okay, C prior is nothing but CSI, C grade plus C normal. Now additional losses also they discussed the loss of the pose with respect to poses and ground truth poses, along with predicted poses and ground truth poses T and G over every BA iteration with increasing weight gamma 0.9k, where k indicates the kth BA iteration. Now what is the limitation? Here we utilize the 3 video frames on the left and their corresponding estimated camera paths, and a reconstruction on the right. Our method can lose tracks in cases where an object is moving, dominate the entire video, which is top rows. Our approach here is struggled in cases where object motion and camera motion are collinear, such as self video in the bottom row. Means from here we can understand that our thing is fails when moving objects dominate, or our fails when object or camera move collinearly. Now camera tracking and consistent video depth. Here we input is a video which has a frames, which has converted to frames, and let's take a 2 frames I and j which are passed to our network. Then we are getting u and w and ui, which are passed to differentiable BA optimization algorithm to get the poses, depth map and focal length, which are updated at every iteration. Here from left we estimate camera pose, focal length and low resolution depth map from the input model through differentiable bundle adjustment. The network iteratively updates these state variables by learning to predict low resolution flow UJ, confidence and movement probability maps WJ. Here UJ is nothing but low resolution flow and confidence, and probability maps WJ is nothing but a probability map, and minimizing weight reprojection to U and WJ. introduced by ego motion using. We also initialize the disparity with mono depth predicted from off self models. Here right in includes consistency video depth module. We fixed we fixed estimated camera parameters and perform first order global optimization over video depth corresponding uncertainty parameters by minimizing flow and depth flow through pairwise 2D optical flows. Here depth and uncertainty are passed to CVD as a flow and flows to get the update in both depth and uncertainty at every step to update uh, to get the poses and focal length. I mean to input a pose and focal length, and we get a consistent video depth for that. These are the results. Here ATE, RTE and ATE we already discussed what is meant by ATE. ATE is they are metrics, absolute trajectory error, relative translation error and rotational error, which are metrics over a validation datasets, Sintel, die check and invalid videos, which are results over these calibrated ATE, RTE and RRE, uncalibrated ATE, RRE. Here existing models aid compared to existing models and this paper model we can see its camera estimation over Sintel dataset it performing good with respect to both time and this metrics, and the second table shows the qualitative comparison of same camera estimation on die check dataset, second type of dataset, which is also performs better in a low time of 0.8 seconds. And third table describes the qualitative comparison of camera estimation on in the wild footage. Qualitative here also it performs taken a less time. Then now last table 4 describes the quantitative comparison of video depth. Lower is better for absolute resolution and log RMSE, real and log RMSE, and higher is better for delta 1.25. Here absolute resolution, log RMSE and gamma 1.25 checked for both Sintel and die check with existing models and this MegaSaM model for both Sintel and die check datasets. Metrics, I mean for both syntax and die check datasets, they used absolute real log RMSE and delta 1.25 metrics over existing models for qualitative comparison of video depth. Now these are the results. Here scenes are dynamic and these are the camera estimated camera trajectories. Here red dash indicates our camera estimate which deviate less from the ground truth camera trajectory, which is a blue solid line than all other baselines. With here on top left alley 1, middle block and dog running, ambush 4, pillow and grill spinning. Here blue indicates GT module and casual LM, Leap Vivo, Particularism, AECO and MegaSaM. Ours is nothing but MegaSaM. These are the with respect to Sintel dataset, die check dataset and invalid dataset. For each dataset, we are here we are estimating camera trajectories for a dynamic scenes, where red line indicates the camera estimates and blue line indicates the ground truth camera trajectories. Now these are the visual depth maps, CVDs. Visual estimate from both MegaSaM and casual SAM and MonoSAM by visualizing their depth maps. This is the ablation study on Sintel dataset where without mono initialization, without MI, without two-stage training means static training and dynamic training. First stage is static training, second stage is dynamic training. First training will give the pose map, depth map, and focal length. Pose, depth map, and focal length, which is iterated over PA, and second step include second step will give the probability map, um, probability mask, motion probability mask. This is the how the example how models will give the output when an input video is given. Here input video is converted as a frames, then they are projected to get the 3D scene, which are projected to get the 3D reconstructed image, which is done by Casual Sam, Monosphere, and ours. We can see our model. I mean, ours is nothing but MegaSaM model, which reconstructed better when compared to both models. Here, Casual as well, Sam also predicted similar when compared to um, MegaSaM, but it slightly fails during motion during motion at some stage. But here MegaSaM overcomes that problem to get the accurate result over it with less time. This is the existing MegaSaM GitHub, which consists of depth anything, and video.py. Then unit depth and camera tracking, CVD optimal, and evolution depth, which consists of monotoptical scripts and everything. Here it's the paper of MegaSaM, which we already discussed, training and equation. Then here they already given how to install the external for unit depth and instruction. Just follow as instruction to run the MegaSaM model. They also given the depth and checkpoints and download running MegaSaM over on both evolution datasets, validation datasets, our Sintel and die check. We can load a existing pre-trained checkpoints to check validation over this both Sintel and die check to get the camera poses and depth for that. Now let's dive deep to project page, how the our SM MegaSaM will work for interactive results. Here they virtually do any video. I mean, they work for both static and dynamic scenes. Let's see. Take this scene. See, we can see here 3D constructed over that image. We can clearly see. We can also see view all points. We can here see how the motion is going on. Every motion of an object. We can see a movement over the object. This is the advantage of this form. Within less time in computing, we can see it's the butterfly which is reconstructed as a 3D scene. We can see visual form with the movements of every movement with all frustration and all points. We can see Here we can't see motion, but we will see now motion with every along with the depth map. Now we are showing the first station with projection thing. Thank you. This is the MegaSaM paper. You have any further doubts, you can reach you can read paper. Thank you.